One moment. I'm trying to find the window with my Chrome. Oh, yeah, it seems I see it. So currently you should be able to see my screen. Oops. What I have here, like on the previous call, I've written for me like a few questions you asked, and like the first one was about like why Lagrangian equals kinetic energy minus potential energy in classical mechanics. So that was like the first question to be discussed here. So I made a small note about this here, and also I read more about like action and what is this, a little bit about history, and prepared a few links about that scene also. Yeah, just the explanation about independence of Q and Q dot. And the final theme is symplectic manifolds. I haven't managed to describe the normal modes like and make the note about those, but anyway, like let's take a look what I have here. Me myself, I kind of also do not remember everything here because I've been doing that bit by bit of the week. So yeah, I will share these notes with you in the chat, probably in the chapter chat. So those will be preserved for the all future generations on the Portal Book Club. Anyway, like the basic idea for me about this kinetic minus potential energy in Lagrangian in the classical mechanics is like about probably like I think intuitively I've been thinking about that. It's like first of all, when you are deriving the Lagrangian for the one particle in classical mechanics by like using the Galilean principles, you can show that this Lagrangian could depend only on the absolute value of the velocity, or v squared, and therefore and you can also deduce that it should look like something like cv squared for some constant c, and Landau just takes it to be equal to the half of the mass of the particle, where and basically that's how he comes to the conclusion that in the absence of forces and any of how to say it, like not boundaries, like linkages between different particles, like more complex systems, so you have just empty space and one particle traveling through it, you will have just Lagrangian equals to k, to the kinetic energy. And in the for any Lagrangians we have some freedom, and therefore we can modify any classical mechanics Lagrangian using the next two procedures. First of all, we can multiply everything by arbitrary constant, and that's kind of equal to change in scales for all of the systems because of the additivity principle for the Lagrangians. So basically, if you have like two different isolated systems A and B, then the total Lagrangian of the two systems will be LA plus LB, and therefore that multiplication is kind of sort of as multiplying every existent Lagrangian in the physics by some constant. So basically it's kind of changing the measurements units or something. And we can also add the total derivative with respect to time of some function of the time and coordinates fqt to the Lagrangian. So if you take any function of the coordinates in time, you can take the total derivative of it by the time, so df by dt, and just add it to the Lagrangian, and that will not change the Euler Lagrange equations. Basically, the evolution of system will be preserved. Yeah, and after like saying that Lagrangian for the one particle equals to the kinetic energy, like basically that one half of mass use the first principle here, so we just kind of choose our units, so C equals to that constant here. Yeah, and after that Landau does the next thing. He says that now if you have some kind of a system where we have a lot of particles and there are some interaction between the particles, then usually we can thought about those like how to say that, not blockages, but like we can think about the interaction between particles or linkage, maybe some ropes, I don't know how to describe it intuitively, but we can describe it in terms of the potential energy. So, and actually it's not only like the connections between particles, but it's also about conservative forces actually, like gravitation, for example. So basically we will have like potential field for the gravitation, and it means that that energy could be kind of transformed into the kinetic energy. So like intuitively for me it seems that we kind of describing yeah, so I have it here. So basically if you put a plus here you will obtain the Hamiltonian, like the full energy, and full energy will be conserved always, so it's kind of constant and just that doesn't change. But if you put that minus here, then it's kind of the amount of energy transferred from the potential to the kinetic one. So to me it seems like, I'm not sure if my intuition here is right, but I've been thinking about that like potential energy, like its intuitive sense is covered or undercovered in the word potential actually. So it has the potential to be freed into the motion energy, like into the kinetic energy. And in simple terms it seems to me that like the minimization of action is just the minimization of energy fluctuations over the system's history. So basically like while system evolves or like particle moves in the field or something, then some portion of the potential energy gets converted into the kinetical energy, or vice versa. And basically that minimization of action tells us probably that the overall fluctuations or changes in the energies should be minimized in the classical mechanics. And I think that is why we have that formula for the Lagrangian here, like k minus u. Yeah, and there is also a great article about the same topic here, and you can see that like the guy there, he will just say to us that basically we need to have like t minus v there because like it's kind of natural variant of kind of monitoring the energy fluctuations or something. So probably that's it, yeah, about this question. If you have some comments, please say. Okay. Yeah.
Probably take a closer look at this after you link it, but thanks for putting it together.
Yeah, welcome. Yeah. Like I wouldn't go like to the article that, or maybe I should. Let me take a look what we have here. So on the graphic here you can see like the overall energy conserved and the energy fluctuations going on while time flows. So basically it's kind of like harmonic oscillator here, where energy oscillates like from full potential energy to the full kinetic and vice versa. Yeah, and for some reason I have copy pasted that text here from the article. So he's saying here that these numbers aren't just telling you about energy. Potential energy is a function of position, while kinetic energy is a function of velocity, and both of these are important to the motion of system. And I see in those sentences kind of the like kinetic energy is like about the dynamics, and potential energy looks to me like about the statics. So basically we're combining those together, and one part is describing the motion and the other one the like potential to motion preserved in the coordinates basically. Okay, and in fact if you're dealing with conservative forces which have a well-defined potential energy everywhere, like gravity, they are the only things that matter. If you want to know how a system is changing with time, looking at changes in energy is a good place to look. If you just add the two, you get the total energy, and that will not change. So instead we subtract the two to capture changes in potential and kinetic energy. So yeah, basically that's what I've been talking about previously. Yeah, also there is really interesting there are a lot of really interesting materials in Wikipedia about the action and the history of doing it. So I, for example, never know that kinetic energy was called vis viva, like the vital force or something. And actually, in the past, there were a lot of the debates what is more crucial, or in the core, how to, like more important, or at the core of everything in physics, like the conservation of momentum or the conservation of the energy. And there was this fight between theorists and engineers, where engineers were using more the conservation of the energy because it was easier to use in calculations, and scientists or theoretical physics, they were using like conservation of the momentum. Yeah, and here I just described it like it's just the machine or functional, like integral, right, which accepts the trajectory of the system and deliver you the real number as an output, and is stationary for all known physical systems. Probably I just taken it from Wikipedia, it seems. And action has dimensions of energy time or momentum length, and its unit are joules second. Action follows from the Hamilton's principle, which is the way of converting local problem of finding equations of motion from the differential equations to the global problem of finding those from minimizing the integral equations. Yes, so like basically like the Newtonian mechanics is formulated in terms of the differential equations, and it's kind of a local picture. And by using Hamilton's principle, we go to the like integral laws, and minimizing that integral kind of give us the global picture instead of the local one. And we can deduce the local picture from the global one using the Euler-Lagrange equations. And that's interesting because I've even seen some parallels in the programming here through the category theory, basically, because like in mathematics, like category theory is also kind of reminds about the Lagrangian approach, so it's kind of more global approach of like deducing things. Yeah, something like that. So probably I should include that link here, just for the interested people. Okay, so and you can read more about the like those controversies, origins, and the things about like kinetic energy and action by the links here. Okay, and about the independence of Q and Q dot, I've just included some Stack Exchange links here, and we have like a simple one here, simple answer, which kinda I was happy with. Yeah, I'm recalling that. So basically, he says here like you have like the action like that here, depending on like position, velocity, and time, and you kind of want to minimize that integral using like different trajectories for a system. But like, do you know a trajectory? No, you do not know it. You need to kind of find it. Yeah, and so first of all, you need to pick the time, like the initial and the final time, basically. And now you know only like the beginning and the end point of the trajectory. But yeah, and now you kind of starting to pick up the random different trajectories for the R here. Uh, yeah, and at this point, like the yeah, so basically here he is talking about that, like you kind of uh, brute forcing or making like different choices for the position and velocities here like independently. So basically you picking just like different combinations of the position and velocities, and therefore like forming up different all of the different trajectories, and just trying to minimize that thing here called action. And by these three selections, you choose a segment of trajectory which passes at the time t through the position r and continues for the interval dt in the direction of v. Yeah, so basically he talks about like the local like situation in one point where you kind of brute force in different directions in the space, right? And different positions. Okay, and therefore you have like sevenfold infinity of choices of trajectories, like at every new point of time. So you kind of going through all of the different variants, and not only in terms of the velocities, right? Like the direction of your movement in space, but also yeah, but it seems to me that's kind of all. So basically, to make a new trajectory, you just need to put some initial point and a final point, and then just try and yeah, like make just different all the different trajectories from the point A to point B. Yeah, so basically he just saying here that those things are independent because like we have this freedom of like building trajectory from the scratch basically here, and that's why we can consider those like q and q dot as two independent variables for the Lagrangians. Yeah, there is one more like more complex link here. Yeah, and here he says that like you can choose position and velocity independently as initial conditions. That's why the Lagrangian function treats them as independent, but the calculus of variation does not vary them independently. Variation in position induces fitting variation in velocity. So yeah, basically their variations are connected by but while you're doing those like brute force things and choosing initial conditions, you can choose those independently because you kind of don't have any trajectory at that moment. Yeah, it seems that the answer is a bit vague, but anyway, I think while if you sit more and think about that and read those, I think you will understand more. Uh, like currently, I'm not sure if I have understood that, but yeah. Anyways, some bits of information could be taken from those two links. Maybe you have something to say about the action and independence before I continue with symplectic manifolds.
Well, I think that last comment about how the variational calculus does not treat them as independent, but the Lagrangian does. I think that comes out of the fact that in order to get the Euler-Lagrange equations, we have to actually integrate by parts, and I think that's what takes care of the dependence of Q and Q dot.
Yeah. I think I'm kind of recalling something from the Landau book.
Yeah, so it's like when you do your variational derivative, you end up with two terms, and one of them is actually like a time derivative of the Lagrangian with respect to Q dot. And so what you can do is integrate by parts, and that removes the dependence. So then both of those terms have a single variation, like delta Q.
Yeah, I will try to open the book at the right page. It's probably somewhere here.
Yeah, this is
Like if you have your action and you have some function of the coordinates here, then the variation of it will be described like this. And we need to have this condition that at the initial and the final time the variations are zero, right? Because we are kind of fixing the initial and final points. And now we can describe the change in the action as the difference of two integrals, and after decomposing it using the Taylor expansion, right? We will have something like this as a result.
Yeah, so this is the part that I'm talking about. That equation that you were just looking at with the delta Q dot in there. If you integrate by parts on the delta Q dot, then you can pull out a delta Q.
Yeah, and you will have this one Euler-Lagrange equations here under the integral, and you will have this dl dq dot by variation of Q.
Yeah, and what the boundary terms there do is what happens in variational calculus is that you're given the boundary conditions. So any variation that you apply has to be zero along those boundaries.
Yeah, and that's this equation 2.3 here. So at T1 and T2 they equal to zero, and therefore the first part of it just goes to zero. I mean, of the equation 2.5.
Yeah, I see. So this is what I was mentioning about how you can get rid of the dependence on the variation of Q dot.
So basically,
by integrating by parts, now the only variation is in Q.
Yeah, so basically that's the moment where we get rid of the dependence on the velocity on the coordinates. We just move into the picture where we only depend on the variation of the coordinate function. Yeah, and in variational calculus there will be a theorem that the sin under the integral here should be equal to zero, and basically we will have the Euler Lagrange equations as the result. Okay, so, and the last sim for today is symplectic manifolds, and I have a bunch of different links here. Probably I will go through some of those. Let's take a look at the first one. Whoa, seems too hard for me currently. Okay, so probably I will leave it for for you to read independently. And today I'm gonna show symplectic geometry link on the Wikipedia, and it seems to me really nice because basically, like, we have seen already two kinds of the manifolds in the book. One is Riemannian manifold with the same scene. We have non-degenerate two forms there, but it's symmetric instead of being antisymmetric as in symplectic geometry. I don't remember if metric tensor is closed, but anyway, yeah. So basically, symplectic geometry is kind of the variation or alternative to the Riemannian geometry or something. And also, we have seen one more type of manifolds, but Penrose haven't been talking a lot about those, which are called complex manifolds, right? With J complex structure in it, and those are kind of have some similarities between those or something. So, okay, yeah, and here there is really nice introduction passage on the Wikipedia, which says that we have just smooth even dimensional space, and on this space we have symplectic form defined, and that allows for the measurement of sizes of two-dimensional objects in space, just like the areas. And symplectic form in symplectic geometry plays a role analogous to that of the metric tensor in Riemannian geometry, and where the metric tensor measures lengths and angles, and the symplectic form measures oriented areas. And symplectic geometry arose from the study of classical mechanics, and an example of symplectic structure is the motion of the object in one dimension. And indeed, in that case, we will have like Euclidean plane R2 with the point PQ fixed in there, and symplectic form will be just the area dp by dq here. And yeah, and the area that form will measure for us of a region S will be something like that. And the area is important because as conservative dynamical systems evolve in time, this area is invariant because of the Liouville theorem, basically. And in higher dimension, the situation will be similar, so we will have this formula here for every pair of the coordinates, like the paired momentum coordinate form will be added here, and therefore any volume in the phase space will be measured in terms of the pairs of different directions in the symplectic geometry. So the volume will be measured like this over those bunch of the two forms, the areas. Yeah, and symplectic geometry has a number of similarities with and differences from Riemannian geometry, which is the study of differentiable manifolds equipped with the non-degenerate symmetric two tensors called metric tensors. And unlike in the Riemannian case, symplectic manifolds have no local invariants such as curvature, and this is a consequence of the Darboux theorem, which is a theorem about basically floppy structure Penrose was appealing to in the chapter 14. Yeah, and that states that a neighborhood of any point of the two-dimensional symplectic manifold is isomorphic to the standard symplectic structure on the open set of R to n. So basically, all of those symplectic manifolds are actually isomorphic to the Euclidean, to the open set of the Euclidean to n space, and that's it, locally. Okay, and another difference with the Riemannian geometry is that not every differentiable manifold need to admit a symplectic form. Okay, and for example, every symplectic manifold is even dimensional and orientable. Okay, and there is something about the RAM cohomology. We can skip that. And there is interesting thing about geodesics here, and the parallel between the geodesics and in the Riemannian geometry and symplectic manifolds is what is called pseudo-holomorphic curves. And those pseudo-holomorphic curves are just like the geodesics, but in the symplectic case. And geodesics are curves of the shortest lengths, and pseudo-holomorphic curves are surfaces of the minimal area. And both concepts play a fundamental role in their respective disciplines. So basically, the theory of the pseudo-holomorphic curves, they kind of are used in the string theory, as far as I understand, in what is called like Grobel-Witten invariants. Yeah, and actually that's the word I forgot the name. Like the Keller manifold. I heard about those probably like 10 or 7 years ago, and at the time I wasn't able to understand what it's meant to be like a Keller manifold. But I think that probably they are very they will be really useful in physics. And basically, those Keller manifolds are just manifolds which have three mutually compatible structures: a complex structure, Riemannian structure, and symplectic structure. So we kind of have 3 in 1 here. And I heard that they're really important, but like I don't know the details. Yeah, and basically in this note here I have a bunch of links discussing like first of all why like what is a symplectic manifold really, and it talks about the phase space in terms of just like vector flows over the manifolds, etc. So there are some parallels with the I don't remember where, but we've been talking about like the Lie algebra of the vector fields on the manifold, probably in chapter 14 or 13, probably 14, yeah. So basically, where we can kind of have a Lie group manifold, and therefore like those infinitesimal flows, like vector fields, they will describe the Lie algebra of that manifold. And we'll have the exponentiation there as a way of converting the Lie algebra elements into the Lie group elements. And that's exactly the same procedure taken here, basically, the same analogy. And from like talking about those flows on the manifold, they kind of describe the phase space using those and the evolution of the system. And afterwards, the guy just kind of converts everything into the symplectic language and describes those in terms of the two form, which basically guarantees that we have a clear, nice separation of the momentum coordinates from the position coordinates, and it's basically it. Yeah, and the next note he has on his WordPress blog is about why symplectic form should be closed. And here he also talks about the different kinds of the manifolds, like Riemannian, almost complex, and symplectic, and he talks about curvatures there and different parallels between the different manifolds notions in mathematics. Yeah, and like more information could be found in those nice book by the Arnold, like Mathematical Mathematics of Classical Mechanics, and also a nice material about symplectic structures is in his book about caustics and wavefronts. But it's kind of involved, and I think that we don't need such details for now, so just include it for future use. Phew. yeah, so that's it. That's it for today. And for symplectic manifolds, maybe you have some questions or something to add. So please go on.
So you mentioned it was a mouthful, pseudo holomorphic curves or something. So I know in like relativity, geodesics are the paths of particles that don't have any forces on them. Do we know what these pseudo holomorphic curves would represent?
Let's take a look. Okay, so is a smooth map from a Riemannian surface into almost complex manifold as it satisfies Cauchy-Riemann equation. What? Sounds complex to me. Okay, and they were revolutionized. No, they have revolutionized the study of symplectic manifolds by the work of Mikhail Gromov. I heard about Mikhail Gromov a lot in terms of how huge that figure in mathematics is, okay, but I don't know details about his work. Lead to the Gromov-Vitan invariants for homology. So they just talk about like that they have some connections to the string theory here, okay, and we have something like a J matrix here, which probably Joe was talking about. It's kind of similar to the symplectic form we have seen written by me in the book. So the applications in symplectic topology, compact moduli spaces. Oh, applications in physics, great. Okay. In type 2 string theory, one considers surfaces traced out by strings as they travel along paths in Calabi-Yau threefold. Following the path integral formulation of quantum mechanics, one wishes to compute certain integrals over the space of all such surfaces. Because such a space is infinite dimensional, these path integrals are not mathematically well defined in general. However, under the A twist, one can deduce that the surfaces are parameterized by pseudo-holomorphic curves, and so the path integrals reduce to integrals over moduli spaces of pseudo-holomorphic curves rather than stable maps, which are finite dimensional. In closed type 2A string theory, for example, these integrals are precisely the Gromov-Vitan invariants. Okay, so basically it seems to me that those are used just like a tool to calculate infinite dimensional integrals for the QFT and string theory connected to it, like those Calabi-Yau things.
Yeah, I think this is not something I'm going to understand today. Maybe when I'm like 50, I don't know.
Yeah, I hope it will be sooner. I mean, a lot of material connected to that passage is inside the Penrose book actually, and I think when we will understand the path integral formulation in chapter 26, and we will go further and further to the later chapters of the book, we will understand more about string theory also, and we will hear about Calabi-Yau manifolds also more. So I think in simple terms we will understand that in a year or two when we will finish the book. So I hope that will happen sooner than like when you will be 50. Yeah, so that's it for today, I think. And for the next time, I propose to where is my plan? One moment. I just need to go to the content page of the Penrose book. Yeah, I've been thinking about reading like first 4 or 5. Let's see how much we can do. So like my plan is like to read 10 or 15 or something like pages and go in those chunks for every call, like 10 pages a call, and that's it. And I think that will be like a nice space for us. So basically the quantum particle chapter starts at page 493, So, and if you add 10 pages, it's like 505 or so. So we should read like first 4 subchapters, like till the quantum theory's experimental background included. And I will write the message to the beta chat anyway, and that's the plan for the next call.
Sounds good. Sounds good.